Imagine a busy city of radio towers. Thousands of phones are attaching, moving, and talking at once. Between a cell tower, the eNB, and the core network node that handles mobility, the MME, messages fly both ways, every second. Here is the puzzle that actually matters. If a message goes up from the tower and a later answer comes back down, and then another message goes up again, how does either side know which phone that conversation belongs to? There is no face on the wire. There is no permanent phone number stamped on every S1 control packet. The path is shared. The payloads look similar. Without a label, the MME would be staring at a pile of anonymous envelopes, and the ENB would have no way to match a reply to the right radio connection. Think of a coat check. You hand over your coat, the attendant does not remember your face among 1,000 people. They write a number on a ticket, tear it in half, and keep one piece with the coat. When you come back, you show your half. That number is the only reason your coat finds you again. On the S1 interface between eNB and MME, LTE does something very much like that, but with a twist. Each side keeps its own local number for the same user equipment, the same UE. The first message starts with only the tower's number. The core adds its own. After that, every UE-associated message carries both. That pair is how a shared conversation stays attached to one phone while traffic flows both directions. In this lecture, we will walk the three messages in the classic S1 UE-associated flow, exactly as they appear in a protocol trace. The initial UE message from eNB to MME, the downlink NAS transport back the other way, and the uplink NAS transport that continues the exchange. We will build each message field by field, watch the identifiers appear, and end with the simple rule you can see for yourself once both labels exist. No jargon first, just the problem. Two machines, many phones, messages in both directions, and a need for a claim ticket that both sides can read. The tower is the one that meets the phone first. When a UE needs to talk to the core for attach, service request, tracking area update, and similar cases, the eNB does not wait for the MME to invent an identity. It opens the conversation itself. That opening is called the initial UE message, sent from the eNB toward the MME. Watch what it carries, piece by piece. First, the claim ticket from the tower's side, the eNB UE S1 AP ID. This is a number the eNB chooses and will remember for the life of this UE-associated S1 connection. It is local to the eNB. The MME has never seen it before. Its only job right now is to say, when you answer me about this UE, put this number back so I can find the right radio context. Next comes the real passenger in the envelope, the NAS PDU. NAS means non-access stratum, the signaling that lives between the UE and the core, above the radio. The eNB does not need to understand every bit of that payload. It relays it. So the initial UE message is partly a courier service. Here is opaque NAS bytes the MME must process. But the courier also writes where the package came from. That is why you see TAI, the tracking area identity, telling the MME which tracking area the UE is in. And EUTRAN CGI, the cell global identity, pinning the request to a specific cell. Location is not decoration. Mobility decisions, paging, and restriction logic all depend on knowing where this UE appeared. Then comes the RRC establishment cause. RRC is the radio resource control layer between UE and eNB. The establishment cause is a short reason code. Why did this radio connection start? Emergency, high priority access, mobile originating data, mobile terminating access, and so on. The MME uses that hint when it decides how to treat the request. So look at the whole first message as one composed object. On the left of a protocol slide, you might see a friendly list. eNB UE S1 AP ID, NAS PDU, TAI, EUTRAN CGI, RRC establishment cause. On the right, the same ideas appear as information elements in the S1-AP encoding, each with a criticality, often reject. meaning if that IE is missing or broken, the receiver should not shrug and continue. Here is the misconception to kill early. The identifier is not the entire message. Students sometimes memorize initial UE message equals eNB UE S1 APID and stop. The source diagram shows several fields traveling together. The ID is the ticket stub, the NAS PDU is the letter. TAI, CGI, and establishment cause are the postmarks and priority stamps that tell the MME how to handle that letter. Plain language pause. You can now see that the first message does more than carry data. It tells the MME who the eNB thinks this UE is, and where that request arose. The MME receives the initial UE message, processes the NAS payload, and answers. The answer in this example flow is downlink NAS transport, MME toward eNB. Watch the ticket transform. The message still carries the eNB UE S1 APID that the tower invented. The MME echoes it back so the eNB can match this downlink packet to the correct UE context on the radio side. And now a second number appears, the MME UE S1 APID. That is the core's own local handle for the same UE-associated connection. From this point on, both sides hold a cross-reference. The eNB knows, my local ID is A, and the MME calls this same conversation B. The MME knows the reverse. Neither side has to adopt the other's numbering scheme. They simply stamp both numbers on UE-associated S1-AP messages. Inside downlink NAS transport, you again find a NAS PDU. This time, core-originated signaling headed toward the UE, which the eNB will forward over the radio. And the example flow also shows a handover restriction list. That list tells the access network which areas or systems this UE should not be handed into. It is policy writing alongside the identity pair, not a replacement for it. On a decoded protocol tree, you would see the same four ideas laid out as information elements. MME UE S1 APID, eNB UE S1 APID, NAS PDU, and handover restriction list. The human-readable summary on the left and the IE tree on the right are two views of one message. When you study traces, train your eye to map left to right. Every friendly field name should land on a concrete IE. Why two IDs instead of one global UE number on S1? Because each node already manages huge tables of local state. Local IDs are cheap to allocate, easy to look up in that node's memory, and independent of how the peer numbers its world. The pair is a compact join key across two databases. Misconception to catch right here. Some learners think the MME takes over and the eNB ID disappears after the first reply. The diagram says otherwise. Downlink NAS transport keeps the eNB UE S1 APID. The original ticket stub is still required. The MME did not replace it, it added a second stub. Plain language pause. The two sides now have a shared cross-reference. Each keeps its own identifier, and the message carries both. That is the moment the coat check becomes two-sided. Either direction can now point at the same UE-associated connection without guessing. Direction flips again. The eNB has something more to send toward the core, another NAS payload from the UE, or the next step in the same procedure. The message is uplink NAS transport, eNB to MME. Look carefully at what did not change. The arrow reversed. The sender and receiver swapped, but the identity pair stayed. Uplink NAS transport carries MME UE S1 APID, eNB UE S1 APID, and the NAS PDU. No new birth of identifiers, no reset to a single stub. The conversation reuses the join key that downlink NAS transport established. This is the heart of UE-associated signaling on S1. Once the association exists, later messages, uplink or downlink, include the known identifiers so each peer can demultiplex the packet into the right UE context. The notes under a good training diagram usually say exactly that. Retain the relevant UE S1 AP ID for the duration of the UE associated connection, and include the known identifier in subsequent UE associated S1/AP signaling. Contrast this with non UE associated messages on the same interface. Things like S1 setup, reset, or paging setup, flavors that are about the eNB MME link itself rather than one phone. Those do not meet a per UE ticket pair. UE associated messages do because they are about one UE state machine running across two nodes. Walk the three message story as a single animation in your head. Panel 1, only eNB UE S1 AP ID plus NAS and location context, arrow up. Panel 2, both IDs plus NAS and optional handover restrictions, arrow down. Panel 3, both IDs plus NAS, arrow up again. The morph from panel 1 to 2 is the birth of the pair. The morph from 2 to 3 is proof that direction is independent of identity continuity. Misconception. A new direction means a new identity. That would thrash state on every hop and break correlation. The source flow shows the opposite discipline. Identity is sticky, direction is free. Another subtle point, the NAS PDU keeps changing content. Different procedures, different information, while the ID pair stays stable. Students sometimes glue this NAS type to this ID pair, as if they were one object. They are not. The pair names the pipe. The NAS is what flows through the pipe this time. Plain language pause. You can now see the rule for yourself. Once both sides know the connection's identifiers, later messages carry the pair so the conversation stays attached to the same UE. If you only remember one operational habit from reading S1 traces, make it this. When you open a UE associated message, find the two S1 AP IDs first. They tell you which row in each node's table you are looking at, before you even decode the NAS. Let us zoom out and restate the whole argument in a few clean lines. The eNB opens the exchange with an initial UE message. It assigns an eNB UE S1 AP ID, relays a NAS PDU, and stamps location and cause context, TAI, EU Trans CGI, RRC establishment cause. The MME answers with downlink NAS transport. It keeps the eNB's ID, adds its own MME UE S1 AP ID, returns NAS, and may attach a handover restriction list. Later, uplink NAS transport reverses direction but preserves both identifiers beside the next NAS PDU. Identity continuity is the point. Direction is just traffic flow. That pattern is bigger than LTE. Distributed systems constantly invent correlation IDs so two services can recognize one shared conversation without sharing one memory space. HTTP request IDs across microservices, database session handles, RTP SSRC plus sequence context and media, different costumes, same play. On S1, the costume is a pair of UE S1 AP IDs because each side insists on a local primary key. If you are debugging a stuck attach or a dropped NAS exchange, ask the coat check questions in order. Did the initial UE message carry a fresh eNB UE S1 AP ID and sane cell context? Did the first downlink response echo that ID and introduce an MME UE S1 AP ID? Do later uplink and downlink messages still show the same pair? When the pair breaks or one side allocates a new ID too early, the conversation fragments, exactly like losing your ticket stub at the counter. Connect one step further. UE associated S1 AP state is not only about NAS transport. Handovers, context setup, and release procedures all hang off the same idea. A UE connection is a joint object identified from both ends. Master the three-message nursery rhyme in this diagram, and the longer procedures become readable instead of mystical. I will leave you with one open question in the same style of reasoning. What other distributed systems need two local labels, not one global name, to recognize a single shared conversation? When you spot the next one, draw the same three panels, open with one side's ID,
Answer with both, continue with both. The picture travels surprisingly far.